Okay, well, welcome again to Math 315 and our analysis and topology. And this is the final and probably a bit shorter recording for chapter 5. And we've been looking at uniform continuity. And you'll recall that our definition of uniformly continuous, well, it was much the same as it was for continuous, except that the delta we had to cook up has to depend only on epsilon and nothing else. I showed a couple of examples of that. The first one was fairly straightforward. The second one was a little bit harder. I just wanted to include a slightly harder example. Again, I wouldn't expect you to be able to reproduce this example, just to show you how complicated it can get, even with a relatively sensible function here. So we've got the function 1 over x squared plus 2 on the real line, and we want to show that this also is uniformly continuous. When we get to differentiation and differentiability, we'll find a nice condition, a nice way of checking for, or one particular test for uniform continuity, but at the moment we're just doing it bare hands using the definition. So I'll go through this one. It's quite a hard example. Let's see if you can follow through the details. So we're looking at f of x as 1 on x squared plus 2, and this is on the real line. So the graph of this looks something like this. It's at x is 0, it's at a half, and as x gets bigger, it's doing this. And you can see that it's got no parts where it goes very steeply, so where you'd need the delta to depend on where you are with the x. So points that start out close together end up close together, and you can specify the closeness without telling me exactly where the points are. Okay, so here it is. We begin. Given epsilon bigger than 0, we put delta equal to, I'm not sure yet, and we're going to have a bit of a long saga to get there. Then if you take x1, x2 minus x2 is less than delta, you've got 2 points that are close together, and I've got to cook up a delta to make f of x1 minus f of x2 less than epsilon, and that delta can only depend on epsilon. Okay, well, you plug it in and you get 1 over x1 squared plus 2 minus 1 over x2 squared plus 2. And when you put these over a common denominator, you're going to get this one up here minus that one there, and the 2's will cancel, so you'll just get x2 squared minus x1 squared, absolute value. Don't need the absolute value sign in the bottom because this is always positive. So you've multiplied those together. Well, you see a difference of 2 squares, and so you think, well, okay, I'll factorise that. So that's x2 minus x1, x2 plus x1. Now this bit here is fine because this is just the same as absolute value of x1 minus x2. This is absolute value, and so I can replace this with a delta, and then I'm left with this expression here, and I'm going to do 2 steps. I'm going to replace this with a delta. This is less than delta times that, and I'm going to use the triangle inequality on this one. So this is less than absolute value of x1 plus absolute value of x2, and I've still got this complicated denominator here. Now we haven't used the AM-GM inequality for a while, and I'm going to use that now. I'm firstly going to split this up into 2 bits. So I'm going to say this is equal to this term over this. Now whatever this is bigger than 2. And so that means this, and it's in the denominator, so I can toss this bit away and say this is less than this over just that, over the x1. And I can toss this little bit away because this is certainly, well, it's certainly bigger than 1. And so 1 over it's going to be less than 1. So I can toss that one away. And then I do exactly the same on this one. I keep this one, and I'm going to toss this away and write it as absolute value of x2 on x2 squared plus 2. Now, the reason I do that is I'm now going to use the AM-GM inequality that we haven't used for a while. And I'm going to say that this first term here, this is bigger or equal to twice the square root of the product. So that's the square root of 2 times the square root of x squared, which is absolute value of x. So just notice I've used the AMGM inequality there. And that means then if I take x1, absolute value of x1 divided by this one, then that's less or equal to 1 over this thing. So I'm just pulling this term underneath here and this one underneath here and reading it backwards. Now I can do exactly the same for the x2 on x2 squared plus 2, and that's going to be less than 1 on root 2, 1 on 2 root 2 as well. So putting all that back in, the difference between f of x1 and f of x2 is less or equal to delta times. This one is less than 1 on 2 root 2, this one's less than 1 on 2 root 2. I combine these together, so I get 2 on 2 root 2, which is 1 on root 2. So I get delta on root 2, and I'll put that equal to epsilon. So finally then I can go back and say my delta then is going to be just root 2 epsilon. And that depends only on epsilon, not on the x naught. So my conclusion is, therefore, this f is uniformly continuous. On the real line. Now that's quite a very hard example, and I wouldn't expect you to be able to do that from scratch. That I had to think about that on myself. That was quite a difficult example there. Well, I want to just finish off this chapter by introducing this idea of a Lipschitz condition. And again, it's an important idea in lots of parts of mathematics. There's these things called Lipschitz conditions, especially in the area of differential equations and so on. So suppose we've got a function f that satisfies the following condition. It says the absolute value of f of x minus f of y, it's less than something times x minus y, where L is some fixed real number. This has got to be true for all x and y in the domain of f. So if we've got a function that satisfies this condition, then it's called this condition is called a Lipschitz condition. We say that this function f satisfies the Lipschitz condition. So it says f of x minus f of y in absolute value is less than some fixed number times absolute value x minus y. And we'll see why this is a useful thing, because we'll see shortly that a nice connection between the Lipschitz condition and uniform continuity. So just as an example, we're going to firstly prove that this function f of x is 4x minus 7 satisfies the Lipschitz condition. I've left a little s out there. Satisfies the Lipschitz condition. So here's the proof of that one. We've got f of x is 4x minus 7, and I want to show that f satisfies this Lipschitz condition. So what we do, well, we do what the thing says. We look at f of x minus f of y. So I plug it in, I get 4x minus 7 minus 4x minus 4y minus 7. Now the minus 7 plus 7 cancels out, so I just get 4x minus 4y. And I can pull the 4 out of that, so I get 4x minus y. Now the Lipschitz condition said that this had to be less than some number times x minus y. Well, I'm just going to say 4 is less than 5, so I'll put a 5 here. I could have put 100, I could have put 7, anything you like, as long as 4 is, as long as it's bigger than 4. So I'm going to say this is less than 5 times x minus y, and that means that f satisfies a Lipschitz condition. And you can see this will work for, you could generalize this, this will work for really any straight line will satisfy a Lipschitz condition. Well, why is the Lipschitz condition interesting? What connection has it got to do with our uniform continuity? Well, in this last example, we're going to prove that a function f which satisfies a Lipschitz condition is in fact uniformly continuous on its domain. So once I've got a function which is Lipschitz, then it's automatically uniformly continuous on its domain. And the proof of that actually is fairly straightforward. and I'll finish with having a look at that particular problem. So here we have f satisfies a Lipschitz condition. So that means that f of x minus f of y is less than L of x minus y for some L and for all x, y. Now we're asked to prove that this f is uniformly continuous. And we prove that in the usual way. So we're going to say, given epsilon bigger than naught, we put delta equal to, and this delta can only depend on epsilon, nothing else. So now remember, L is a fixed number; it's not changing. So you've got some particular fixed L. So if the absolute value of x1 minus x2 is less than delta, then the absolute value of f of x1 minus f of x2, well, we were given that it's less than L times x1 minus x2. I've just simply used the definition of what we mean by a Lipschitz condition. And this bit here is less than delta, so this is less than delta L. I wanted it less than epsilon, so I at this stage put this equal to epsilon, and I'm just going to make delta the subject, and so I have epsilon on L. Now L is a fixed number, so this delta depends only on epsilon, not on the x and the y's. And so therefore we can say f is uniformly continuous. And that's the end of that section. And so I thought I'd cut it a bit short at this stage. I think we've probably done enough for this chapter, and we'll continue on in chapter 6.